So moving ahead, okay, so we'll see the interpretation of Laplace transform and how it is related to the Fourier transform. Okay, so let's take an example. So I'll take an unit step signal which is defined as 1 for t greater than 0 and 0 for t less than 0. Okay, and it's discontinuous at t equal to 0 because the left hand limit and the right hand limits are both different. Okay, so now if I take the conditions for existence, okay, so let's calculate what is mod of x of t for this. So mod of x of t for this, so x of t is equal to u of t dt, right? It is 0 for t less than 0. If you split this, so minus infinity to 0 minus mod u of t dt plus 0 plus to infinity u of t dt. Okay, so mod doesn't matter because u of t is a positive function. It is 1 or 0, right? So for for t varying between minus infinity to 0, right? So this integral is 0 because u of t is 0 and this is 1. Okay, and when you integrate 1 with respect to t, what do you get? You get dt. Okay, with respect to t you get t, right? And if you apply the limits, so you'll get infinity minus 0, which is obviously infinity. Okay, so which means the area under mod x of t dt for if x of t is equal to, this is just one specific example. Okay, so this, if you use this condition, so this is tending to infinity. Okay, now let's see what Laplace transform does. Okay, now I'll take a general signal. So let x of t have a Laplace transform x of s, and by definition x of s is defined as, okay, integral minus infinity to infinity x of t e power minus st dt. Okay, now I'll use the same condition. Now mod of x of s. What is s? S is a complex number, so x of s in general will be complex. Okay, so if I use the law of triangular inequality, use the same steps, repeat the same steps. Okay, now all you have to do is, so instead of being the product of two numbers here, x of t into mod this one, z1 into z2, you get product of three numbers. Okay, so it doesn't matter. So the product of complex numbers will always have the product of lengths. Okay, so it doesn't matter how many terms you multiply. So the length of if z is equal to z1 z2 z3, the product of three complex numbers, so the length of vector z is equal to the product of individual lengths. Okay, so it doesn't matter whether there are two sides or three sides, or three complex numbers or four complex numbers, right? So the product of lengths will give you the product of the length of the products. Okay, now if I take the mod, this I can split it and write it as e power minus sigma t into e power minus j omega t dt. Okay, so by the same steps, if you repeat, right, so mod of e power minus j omega t is equal to 1, you get a condition for existence of Laplace transform. Okay, so mod of this into mod of this, right, you can use them separately or you can merge them, okay, because both are equal. So repeat the same steps. Okay, so I will arrive at this relation. Okay, so this is the condition for, sometimes the word used is convergence. Okay, existence or convergence of a Laplace transform. Okay, now so we saw that we'll take the same example, u of t. Okay, we saw that u of t the integral u of t dt, right, so will tend to infinity. Now we'll see what is the, if you notice the difference between equations of existence of Fourier transform and Laplace transform, there is this extra term in the condition for existence of Laplace transform, e power minus sigma t. So now we'll see the significance of that. Okay, so now if you draw u of t, okay, so you'll get the signal like this, so which is 0 here, and this is a signal. Suppose if I multiply it with the signal, so let's say e power plus 2t when sigma is equal to minus 2. Okay, now let's see what will happen. Okay, so if you draw this, so at t equal to 0 you get u of t into e power 2t, right? So for t less than 0 the product will be equal to 0. For t greater than 0, right, it starts from 1 and it goes on diverging. Okay, so now this area was infinity, right? This area is obviously infinity, it doesn't converge. Okay, because when you multiply e power 2t with u of t and calculate the area under the curve, okay, so this is what you are doing, right? In case of u of t, you are calculating area under this curve. Okay, now obviously this will go to infinity like this, so this area is obviously larger than this. If this is infinity, this has to be infinity, there is no other way. Now I'll take other value, okay, sigma equal to plus 2, right? What will happen? So if you take now x of t equal to u of t, right, and if you draw u of t into e power minus 2t, okay, what will happen? What do you get? You get this signal. Okay, it starts from 1, it is 0 here for t less than 0, and you get an exponentially decaying signal, and ultimately as t tends to infinity this goes to 0, so the area under this, if you calculate, it will be something finite. Okay, and this area is given by what? This term. Sorry, since u of t is there, I am going to make lower limit equal to 0. Okay, okay, since sigma is a variable, you can select the value of sigma. Okay, you can select sigma equal to 1. Okay, if you select sigma equal to plus 1, so you'll get this curve. Okay, so it will go to 0, but it will decay slowly, more slower compared to when sigma equal to 2. Okay, but the area will still be equal to finite. So if sigma is equal to minus 1, then it will go on exponentially growing, then the area will go to infinity, right? So you understand what is happening here. So what you are doing is, so you have the flexibility of choosing the value of sigma, right? So what sigma does is, sigma basically dampens the signal x of t. Okay, so when you select the value of sigma appropriately, right, so basically you can, by selecting the value of sigma appropriately, you can make the product x of t into e power minus sigma t converge. Okay, and this is one of the main advantages of using Laplace transform. Okay, even if the Fourier transform doesn't exist, okay, the Fourier transform for u of t exists. Okay, but there are some other functions where the Fourier transform doesn't exist, but you can make the Laplace transform to exist. Okay, just as an example, you can take x of t to be equal to e power 2t u of t. Okay, so the Fourier transform for this signal doesn't exist, but you can, the Laplace transform exists provided sigma is greater than 2. Okay, right? So this is what that condition will give us. Okay, so now notice that sigma is not equal to 2 here. Okay, so the signal x of t itself is e power 2t into u of t. Sigma you can select. Okay, so this is where the concept of region of convergence comes. Okay, fine. So region of convergence is nothing but these are those values of sigma, okay, for which this integral will be less than infinity. Okay. Fine. So we'll solve an example, okay, and find out the existence. Okay, we'll take x of t equal to e power 2t into u of t, for example. I'm sorry. Okay. explanation. Okay. Okay, so let x of t is equal to e power 3t into u of t. Okay, so find the Laplace transform. Okay, so the Fourier transform for this definitely doesn't exist, because the this integral will tend to infinity. Okay, so if you draw it, so it's exponentially growing exponential signal. Okay, so it starts from t equal to 0 with 1 and it grows exponentially, and if you calculate the area, obviously it's going on increasing, and as you reach t equal to infinity, the area would have been more than right. So we cannot say more than infinity, right, because nobody knows what infinity is. So obviously it's an indeterminate area. Is very large. Okay, it's infinite. Okay. Now what I'm going to do is I'm going to try and find the Laplace transform of this. Okay, so I know that x of s is equal to, I'll use the definition, minus infinity to infinity. So I have the habit of writing this unless and until you get some good practice, equal to this. So this I will write it as, so since it's a product multiplied with u of t, so I split it into minus infinity to 0 minus, where the product goes to 0, so I won't write it again and again. So u of t, there is no need of writing u of t for 0 to infinity, because u of t is equal to 1 for all values of t greater than 0, right? So product will be equal to e power 3t into e power minus st dt. Okay, so this I'll write it as e power minus of s minus 3t dt. Okay, so what is the integral of this? It is minus of 1 by s minus 3, okay, e power minus s minus 3 times infinity minus e power minus s minus 3 times 0. Okay, now suppose if s minus 3 is less than 0, right? So which means negative, so minus into negative quantity will be plus, plus into infinity will be plus infinity. So e power plus infinity will go to infinity, right? So it doesn't exist. Okay, so s minus 3 has to be greater than 0 for this integral to exist. Okay, so if s minus 3 is greater than 0, so s minus 3 into infinity is infinity, minus of infinity minus of s minus 3 into infinity will be minus infinity, e power minus infinity will be 0. So this will go to 0 provided s minus 3 is greater than 0. Okay, fine. So as t tends to infinity, we have seen, so if it's an exponentially decaying signal, the value will go to 0, right? So as t tends to infinity. Right, so that is what I am using here, and this value is obviously equal to 1. Okay, so 0 minus 1 is minus 1, minus into this minus will be equal to plus, so this will be 1 by s minus 3. Okay, and when does this Laplace transform exist? This Laplace transform exists only if, what is that condition? So I have x of t, which is e power 3t into e power minus sigma t, right, dt is less than infinity. Okay, and when will this be less than infinity? When e power minus sigma minus 3 into t, right? So this integral has to be, right, so there is u of t also, so I am going to change the lower limit to 0. Okay, so this is from the condition for existence or convergence of Laplace transform. Okay, so this integral has to be less than infinity. So when will this be less than infinity? When sigma is greater than 3. Okay, right? Okay, so this will give us, so if you draw the complex plane, okay, look at the complex plane. So this is real part of s, which is sigma axis, and this is imaginary part of s, which is the j omega axis. Okay, now you see that. Okay, so the convergence condition doesn't depend on the imaginary part. Okay, it depends only on the real part. Okay, so suppose this is sigma equal to 1, sigma equal to 2 and sigma equal to 3 for a given signal x of t equal to e power 3t. Okay, now sigma has to be greater than or equal to 3, right? Basically greater than 3. Okay, so now right, for all these values of sigma here, right, sigma or s. Okay, so for example, if I take this 4 5 and plus j1 j2, okay, so if I take some random point, okay, so this will be some 6 plus j2. If I evaluate x of 6 plus j2, okay, so my Laplace transform will exist. Okay, so all you have to do is substitute 6 plus j2 in place of s, right? So 6 minus 3 will be 3. So 1 by 3 plus j2 will be the Laplace transform. 1 by 3 plus j2 is something finite, so obviously the Laplace transform exists. Okay, but if you select the values of s from this part, okay, so this extends from minus infinity to plus infinity, right? So this, all these values, okay, all the points s that come in this shaded region are called as region of convergence. This region is called as region of convergence, and it is a set of points which are present to the right of values sigma equal to 3, right? Because these are the points where if you calculate the Laplace transform, it will be something, definitely something finite. Okay, now so this part, okay, so I'll use some other color, right? So if you select any value from this part, the Fourier transform, the Laplace transform may exist or may not exist. Okay, so we will not be sure, hence we don't include these points. Okay, now right, so which means the Laplace transform may go to infinity. Okay, and whenever you evaluate Laplace transform on this line, so this will be equal to nothing but your Fourier transform x of j omega, where sigma is equal to 0. Okay, so Fourier transform is nothing but basically Laplace transform evaluated on the imaginary axis. Okay, with s equal to j omega only, with sigma equal to 0. Okay, now since in this case j omega axis doesn't lie in the region of convergence, which means if you evaluate the Laplace transform on this line, so the Laplace transform may go to infinity. Okay, hence the Fourier transform for this signal e power 3t into u of t doesn't exist, whereas the Laplace transform exists. Okay, fine, we'll stop here.